So now that we know what functional dependency means, there are some axioms or a set of rules, inference rules, that can be inferred from those functional dependencies. And we're going to talk about those right now. They're called Armstrong's axioms. So the first axiom is called the axiom of reflexivity. And it basically says that if Y is a subset, so the C with a line under it means subset. So if Y is a subset of X, then X determines Y. Now, let's see a live example of that to see what it means. Let's say I have CSC 121. And if I look at CSC 121, that consists of two parts. It consists of CSC, which tells me kind of the department offering the course, or what kind of course it is, that it's a computer science course. And then it consists of 121, which is the course ID, and it also kind of tells me that this is a 100-level course. So this course number, okay, let's call that X, consists of two things: the department offering the course and the course ID. So if I know that the department that's offering the course is a subset of the course number, that means if you give me any course number, I will be able to tell you the department that's offering it. So if you give me Math 167, I will know that the department offering it is Math. If you give me ENG 101, I will know that that's offered by the English department. If you give me Bio 111, I will know that it's offered by the Bio department, the Biology department. So here, this is called axiom of reflexivity. And because this X contains a lot of information, I can determine things from it. So because here, the course number, the department and the course ID are part of the course number, that means the course number determines the department and determines the course ID. So that is what this axiom is saying, that if Y is a subset of X, then you can, if you give me X, I will be able to tell you Y. There's another axiom called axiom of augmentation. If I know that X functionally determines Y, and you give me X and Z, then I know that it determines Y and Z. This is called partial dependency. And when we start talking about how to do normalization, these axioms will come into place and we'll refer to them. That's why we're kind of covering them now, and then we're going to refer to them later in the following classes. So let's look at an example here. If I know, for example, that the banner ID determines the student name, address, grade, for a course, a specific course. So let's look at this table, sorry. So this table is storing the banner ID of a student, their name and their address. And then it's also storing each course they took, the grade they got, and when they completed the course. So if I look at this table, I would have to have two attributes become my primary key: the banner ID and the course. If you tell me the banner ID and the course, I will be able to tell you the name, the address, the grade they got for the course, and when they completed this course. Now here, I have a partial dependency. The student name does not depend on the full primary key. It only depends on the banner ID. The student address only depends on the banner ID. So we call that a partial dependency. I already know that banner ID X determines student name. And so when you give me a composite primary key, banner ID and course, I still know that it determines the name and, of course, the course. So this is called a partial dependency. It's called axiom of augmentation. If I know that something functionally determines something else and you add a little bit of information to it, I still have that determination that it's still Y. And so partial dependency, when we're able to identify partial dependency, this will become useful because this is one of the things that we will try to avoid when we talk about reducing redundancy. Okay. So here, banner ID and course are both the primary keys. student name and student address are only dependent on the banner ID. They don't depend on what course the student took. And so we don't like this. This is something that's undesirable because we want all attributes to be fully dependent on the primary key. We don't want them to be partially dependent on the primary key. Another axiom is called the axiom of transitivity. And here, if I know that X functionally determines Y and Y functionally determines Z, then really I can go from X to Z. Then I know that X functionally determines Z. Let's look at an example here. We have a table about a student. We're storing the banner ID of the student, their name, their address, the program that they're in, the name of the program, and how many credits they need to graduate from this program. Now, if I know the banner ID, I can determine, what program they're in, right? And if I know the program that they're in, I can determine the name. And if I know the name, I, of course, can determine the credits. But if I think about it, banner ID telling me the student and the student telling me the program ID, and then program ID telling me the program name, that means banner ID is determining the program name. And banner ID is determining how many credits the program is. Well, that doesn't seem right. I shouldn't be able to get it that way. But because the data here is stored in one table, I am able to get it that way. And so this is the axiom of transitivity. I am able to get it because I'm storing all the information in one table. And if we think about anomalies now, if I delete the last student, or I come to insert a student and by mistake I insert the wrong program credits for their program, I'm going to get, an insertion anomaly or an update anomaly or a deletion anomaly. So this is undesirable. If you have transitivity in your table, that's something that is going to be undesirable. And so when we don't want data in our table to be kind of transitively dependent on the primary key. You want it to absolutely depend on the primary key. Now, a couple other rules that are nice to know is the union rule. And this rule just says that if you have two tables that are separate, and those two tables have the same primary key. So I have a table that has a primary key A, and it has some information. And then I have another table A that has another set of information. Well, then we think that the right thing to do for these two tables is to put them together. So for example, if I have a table that stores the social security number and the employee name, and another table that stores the social security number and the spouse name, well, maybe I should consider putting those two together in one table where the key is the social security number, and that tells me the name of the employee and the name of their spouse. So when we're talking about normalization in the next few lectures and videos, we're going to be talking about how we have a huge table and we want to split it. But we also want to keep in mind that we don't want to oversplit. So if you go down to a situation where you've split data and both those two tables have the same primary key, then you need to ask yourself if you've split too much. Because if the primary key is determining the data in the first table and the primary key is determining the data in the second table, maybe they should have been in one table. Okay. Now, of course, there are reasons sometimes to separate data into two tables, like we mentioned before. If I'm storing information about like an employee and then maybe their passport information. Well, maybe because the passport information, there's a lot about the passport, like the number, where it was issued, the date it was issued, the place it was issued, when does it expire, the visas that are on it. Maybe I don't want to clutter my employee table with this information. So maybe I want to put it in another table. So yes, sometimes we do want to keep things in the same table, and sometimes we do have reasons to put data into separate tables. So of course, nothing is absolute. You always have to look at the use case that you are following and you're trying to achieve with your database design. Another inference rule is called decomposition. And decomposition is the reverse of the union rule. And it just says that if you have a primary key, and in that primary key in a table, that there are two entities that are determined by A. They are functionally dependent on A. Sometimes you might want to consider breaking them up into two tables, and that's the passport example that I was saying. So union is saying that sometimes you might have two tables that you want to put together into one table, and decomposition says sometimes you might have a lot of information in one table and you want to split it in two tables. And again, this depends on the use case and the database, how much information there is. Now, when you're doing the normalization that we're going to talk about, sometimes you might want a dependency diagram. And a dependency diagram is just basically a bunch of arrows that say what functionally determines what. So here I have like a project number, a project name, an employee number, their name, their job, like how many hours they're supposed to be working and charge, and then hours. And so maybe, you know, if my primary key is the project number and employee number, I can see that, you know, employee name really depends on the employee number. So here there's a partial dependency between employee number and employee name. Employee name doesn't really depend on the project number. So here we would say there is a partial dependency between employee number and name. The same with the project number. The project number really, the project name has a partial dependency on the project number. It doesn't depend on the employee. So here I see a partial dependency. And so you can keep drawing these out, and sometimes it helps with normalization. So it's just a technique. Like I'm not going to ask you to do one of those diagrams, the dependency diagram, but if you see one of these, I just want you to know what it is. So let's practice. So you might want to pause this video and answer the question yourself and then unpause it. But basically, I want to know what type of functional dependencies are found in this data. So here I have a table that shows some tournaments, the year the tournament was played, who the winner was, and the birth date of the winner. And I have two columns that are primary key. So I have a composite primary key. Well, let's think here we have a transitivity relationship. I know that the tournament, for example, if you give me the tournament and the year, which are both primary keys, I can tell you who the winner is. Now, if you tell me who the winner is, I can get from the winner the birth date. Does the birth date really depend on the tournament and year? No, but because of the way the data is structured, if you tell me the tournament and year, I will be able to determine the winner. Winner determines birth date. That means if you tell me the tournament and year, I can know the birth date of the winner. This is an example of a transitivity property. So for this classwork, what I want you to do is look at this table. I want you to determine the anomalies that exist. So the insertion, update, and deletion. Think of these three, and I want you to give an example of each one. So say if I insert this data, if I update this data, if I delete this data, what would happen?